Now for stars like our Sun, the collapse continues until it produces a new and exotic type of stuff. Vast expanse of space where time and reality intertwine. One question has perplexed humanity for centuries: what happened before the Big Bang? For generations, the Big Bang theory stood as the cornerstone of our understanding of the universe's birth. But what if that was only the beginning of the story? What if there was a time before time, a reality before the explosion that birthed our cosmos? Stay tuned as Brian Cox reveals something significant in theoretical physics, peers into the abyss of quantum speculation, and grapples with concepts that defy conventional wisdom. Contemporary scientific understanding elucidates the genesis of the universe through the framework of the Big Bang theory. According to this theory, our cosmos originated from the explosive release of energy from a point in space-time known as a singularity, where energy density and mass approached infinity while all dimensions converged to zero. However, recent statements by Brian challenge this theory, asserting that the universe has perpetually existed, rendering the Big Bang theory erroneous. The Big Bang theory postulates the existence of singularity devoid of time, space, or matter. This raises critical questions about the origin of singularity, what preceded it, and the mechanisms that triggered the commencement of the Big Bang. It beckons the query of whether the universe has an eternal existence or if it has a definitive beginning. For scientists, particularly physicists and biologists engrossed in the fundamental essence of life, the quest for understanding takes them to the very genesis. A depiction of the origin and progression of the universe as it stands has been drawn. A recent meticulously precise measurement of the universe's age places it at approximately 13.75 billion years old. Nevertheless, the why behind the universe's inception remains an enigma. Questions about events preceding the Big Bang persist, highlighting the ongoing research in this domain. Based on current understanding, what is certain is that the universe was incredibly hot, dense, and minuscule 13.75 billion years ago. Astonishingly, everything we presently observe in the universe was at some point compressed into a space possibly smaller than an atom. The universe has since expanded and cooled, giving rise to complex structures, including DNA, celestial bodies, and life as we know it. Efforts to unravel these mysteries involve stargazing and the construction of instruments capable of replicating the conditions near the Big Bang. These endeavors seek to discern the origin of the universe and the mechanisms underlying its development. Centuries ago, St. Augustine pondered the nature of God's existence before the universe's creation, concluding that time was a creation of God and there was no before. In the 20th century, Einstein's theory of relativity linked mass and time, demonstrating that time flows differently in proximity to massive objects. Consequently, the concept of time and causality became intertwined. Einstein's viewpoint suggested that discussing events before the Big Bang was futile as there was no before. Nonetheless, this notion challenges the fundamental principles of causality in physics, where every effect has a cause. Einstein's assertion that nothing existed before the cosmic singularity appears counterintuitive as it implies the absence of a past. This raises questions about the validity of such a proposition. Despite ongoing debates, the scientific community maintains strong confidence in the Big Bang theory. According to this theory, the universe isn't expanding into something, rather, space-time itself is expanding. Space and time are thought to have originated with the Big Bang and have been stretching since. Einstein's theory of general relativity, developed in 1915, forms the bedrock of these concepts, supported by real-world evidence like American astronomer Hubble's 1929 observation of the universe's expansion and the American scientists Penchas and Wilson's 1965 discovery of cosmic microwave background radiation. This radiation, appearing 379,000 years post-Big Bang during hydrogen recombination, aligns with the theory. The Big Bang theory proposes that within the first second of its birth, the universe was as tiny as an atom but has gone through 6 stages. According to Brian, these stages, including the Planck, grand unification, inflationary, electroweak, quark, and present-day phases, have significantly influenced the universe's structure and fundamental forces. The Hadron phase, marking a crucial moment when the universe shrank to the size of an atom 1 second post-Big Bang, is noteworthy. At this scale, quantum theory governs classical physics. Esteemed cosmologists such as Stephen Hawking pondered whether quantum theory, which effectively explains subatomic phenomena, could be extended to encompass the entire universe. This led to the birth of inflationary quantum cosmology, hailed by prominent astrophysicist John Gribbin as the most profound scientific advancement since Isaac Newton's era. In essence, inflationary quantum cosmology provides a framework to address the mystery of the cosmic singularity, challenging the classical belief that it was a point with zero volume. However, quantum theory introduces an inherent element of uncertainty at the most basic level of nature, making it impossible to pinpoint the exact moment of the universe's inception or its initial volume. An intriguing facet of quantum theory is its allowance for the spontaneous emergence of particles from the vacuum. Quantum cosmologists pondered whether the universe itself could have arisen from a random fluctuation adhering to the principles of quantum mechanics. If this were the case, the very reason for the existence of something lies in the inherent instability of the vacuum. In the realm of physics, a vacuum refers to a state devoid of particles, yet it is not entirely devoid of properties. Heisenberg's uncertainty principle, a fundamental concept in quantum mechanics, dictates that certain pairs of properties cannot be accurately measured simultaneously. For instance, the more precisely we know the position of a particle, the less precisely we can measure its momentum and vice versa. Another such pair is time and energy. Greater precision in measuring the time of an event results in less precision in measuring the energy associated with that event. This brings us to the notion that a perfect vacuum, where all field values remain constantly at zero, is in direct contradiction to the Heisenberg uncertainty principle. According to this principle, if the value of a field is known with absolute precision, its rate of change becomes entirely random, preventing it from remaining zero at all times. In simpler terms, pure emptiness is inherently unstable, and true emptiness, as we might imagine it, does not exist. According to Bryan, the concept becomes even more astonishing when we consider that a universe comprising billions of galaxies could have emerged from what we typically perceive as nothingness. All mass, as famously described by Einstein's equation E=mc², represents a condensed form of energy. However, this vast positive energy bound within stars and galaxies must be counterbalanced by an equal amount of negative energy stemming from their gravitational pull. In a closed universe with a finite lifespan destined to eventually contract, these positive and negative energies must harmoniously balance each other, resulting in the total energy of such a universe being precisely zero. Stephen Hawking delved into the intriguing question of how the universe might have originated from nothing. He pondered the possibility of creating a celestial body without an increase in its overall energy, given that forming any physical entity requires an expenditure of energy. This line of thinking led to the significance of gravity, which possesses negative energy due to its attractive properties. To separate objects gravitationally bound, such as the Earth and the Moon, energy must be expended. This negative energy could potentially be balanced by the positive energy needed for the creation of matter. However, the scenario becomes more intricate when considering celestial bodies like stars. As a star diminishes in size, its negative gravitational energy intensifies, ultimately surpassing the positive energy inherent in matter. This critical point results in a star collapsing or condensing into a black hole. Paradoxically, a black hole contains positive energy, while empty space remains stable. This implies that objects like stars or black holes cannot spontaneously emerge. Nevertheless, the entire universe can. Quantum mechanics aligns with Stephen Hawking's conclusions. American scientist Alexander Vilenkin demonstrated that a minuscule vacuum filled with energy can spontaneously emerge from a state of emptiness due to negative pressure from cosmic inflation. This energized vacuum rapidly expands, reaching cosmic dimensions within microseconds, emitting light and matter, ultimately culminating in the Big Bang. Consequently, a compelling explanation emerges: the universe originated from nothing. Before this event, there was neither energy nor space nor time. The duration of this nothingness is irrelevant since time did not exist. During this era of nothingness, our universe arose from a random quantum fluctuation of the void. However, it raises the question of whether this quantum fluctuation was genuinely random, echoing Einstein's assertion that God doesn't play dice. This revelation prompts contemplation of its implications and the possibility of another energetic vacuum spontaneously reappearing, triggering a new Big Bang, potentially posing a 100% probability of humanity's obliteration. In the realm of physics, certain fundamental constants underpin all physical laws. These constants include the speed of light, the gravitational constant, Planck's constant, the masses of the electron and proton, and the charge of the electron. Deviations, even slight ones, in any of these constants would render our universe non-viable. For instance, altering the speed of light would disrupt the stability of atoms and stars. The precise tuning of these constants remains a perplexing enigma. Additionally, the question arises as to why our universe is three-dimensional, even though Minkowski's space encompasses four dimensions in the geometric interpretation of the special theory of relativity. Imagine that we reside not in a three-dimensional space, but on a two-dimensional sheet. In this scenario, forces such as light and the strong nuclear force operate solely on this sheet. What if there were another universe, another sheet floating just a fraction of a millimeter away? We wouldn't perceive it because light and forces are confined to our sheet. This intriguing concept challenges our understanding of the cosmos. We now contemplate the validity of this proposition, which suggests the existence of alternate realities and even parallel universes. String theory, with its notion of numerous space dimensions, has gained recognition as the primary candidate for the grand unified theory of everything, including gravity. Its assertion that the universe may contain countless universes provides fertile ground for exploring the pre-Big Bang era and understanding the singularity concept. Nonetheless, this theory's validity remains elusive, as we currently lack empirical proof of the existence of other universes. In conclusion, science has achieved remarkable strides in understanding the nature of the universe and its origins. Still, profound mysteries endure, encompassing the nature of the universe's inception and the existence of multiverse. The notion of an ever-expanding universe from a singular point, whether it be the Big Bang or the Big Bounce, remains the prevailing perspective, yet some posits that the universe has always existed, rendering such theories obsolete. Quantum cosmology, string theory, and inflationary quantum cosmology offer intriguing insights into the nature of reality, and we anticipate that future breakthroughs will continue to expand our understanding of the cosmos. As we explore these mysteries, one central question lingers: are we witnessing the emergence of yet another universe, and if so, what lies ahead for humanity?